Dante Certification Level 2, 2nd Edition. VLANs and Trunks. In prior chapters, we reinforced knowledge that you already gained by working with your home network. Going forward, we will extend that, giving you the skills to better manage medium-sized Dante audio-video networks. In this chapter, we'll talk about structuring a switch with VLANs, which essentially allows a single switch to behave like multiple separate switches. We'll talk about linking switches together with trunk lines and how to transport multiple VLANs on that link. We'll explain what a broadcast storm is, what causes it, and how a protocol called Spanning Tree Protocol, or STP, can help prevent it. Finally, we'll talk about non-blocking architecture, link aggregation groups, and high-speed trunk lines that provide the bandwidth you'll need. So let's start with the idea of a local area network. In this slide, we show an image of a LAN here in the foreground, right? A LAN is simply a group of devices in the same area that can communicate to each other. If I remove the connection between the two switches, I create two islands of communication. Essentially, I've created two separate LANs, right? Well, we can do the same thing with a network switch, and that's what a VLAN does. It's worth noting that ports on the same VLAN do not have to be neighboring ports on the switch. You can randomly assign them any way you like. But when I'm drawing this, I just draw it this way so that it's easier to visualize. Now, let's talk bandwidth for a moment. You'll hear this term, non-blocking architecture. Non-blocking architecture means the switch itself is not the bottleneck. It can move anything that you throw at it. Your only point of restriction is your individual port speed. Now you can calculate whether the switch is non-blocking or not. Let's suppose this switch has 28 ports, all at 1 gigabit capacity. So if we have 28 ports times 1 gigabit speed times 2 directions, because a 1 gigabit port can do 1 gig in and 1 gig out at the same time, that means the switch should be capable of managing 56 gigabits per second of data. If the switch does that, then it's considered to be non-blocking. Now you may also encounter switches that have 1 gigabit ports for the network devices and a few 10 gigabit ports for links to other switches. To determine if this is a non-blocking switch, you could take your 26 1 gig ports times 2 directions, that gives us 52 gigabits of traffic, plus the 2 ports at 10 gigabits times 2 directions. Those 2 ports alone would require 40 gigabits of switching capacity. Add it together, if the switch can move 92 gigabits per second, then the switch is non-blocking. Now, let's talk about where bandwidth bottlenecks can occur. Let's suppose these 2 switches have 1 gigabit ports all the way through. That means each one can manage 28 gigabits per second in and out. When I connect them with a trunk line, that trunk line is only 1 gigabit per second in each direction. So why does this matter? Let's suppose I have 2 devices on that top switch, each one sending about 600 megabits per second. Now that could easily get to 2 other ports on the same switch. However, they would not both be able to communicate to 2 ports on another switch. Together, they would make 1.2 gigabits of traffic, but our trunk line is only 1 gigabit. Now, some people will want to solve that by making 2 connections between switches. After all, that would give us 2 gigabits of capacity, right? Well, that won't quite work. Most switches have Spanning Tree Protocol in it. That will recognize that we have 2 connections between the same switches, and it will put one in a dormant state. So that won't give you more bandwidth. And frankly, if one link wasn't made dormant, then you'd have a different problem. Let me show you. Let's suppose we plug in a laptop and it's set to automatic IP configuration. So the laptop will start by sending a DHCP request, which is a broadcast message. It will go to every port on the switch. Not only does it go to every network device on this switch, but it goes to the other switch as well. In fact, it goes there twice. Now you might say, you know what, big deal. The DHCP request is a very small amount of data. I'm not really losing that much bandwidth. What harm could come of that? Well, let's see how this plays out. The broadcast message that went up one leg goes to every port on the next switch. including the other trunk link from the first switch. And the same happens with the DHCP request from the other trunk link. It will go to every port on the switch and back down the other link. Once it gets down to the first switch, these messages will hit every port on the switch again, including going back up the trunk line again. And this will happen over and over in an endless loop as fast as it can, eating up bandwidth across the network. And this is what we call a broadcast storm. This is the reason that spanning tree protocol exists. It detects and shuts down loops in the network. So now, when the computer sends a DHCP request, it goes to every port on the switch, but the extra link to the other switch is shut down. So now it can't get stuck in an endless loop. So let's get back to this idea of creating two links between switches. The original idea was to get double the bandwidth, right? Well, if that's your goal, you can achieve that by programming these links as a link aggregation group. A link aggregation group instructs your switch to use these two links as one logical path. So you will get double the bandwidth, but you won't get loops in your network, which created the broadcast storms. As we know, when the computer sends a DHCP request, that is a broadcast message that goes to every port on the network. However, the link aggregation group tells the switch that these two ports are being used as one. This is one logical path. So the DHCP request only goes up one side. And when it reaches the other side, since that switch is also programmed to use these two links as a link aggregation group, it knows not to send the signal back down the same cable. Now this is all behaving as it should. Now, as a design feature, link aggregation groups are not limited to 2 cables in a group. I've seen switches that'll do 4 or even 8 in a group. However, even when I'm hitting 2 or 3, I got to start asking the question, should I be using a switch that's all 1 gigabit, or should I have put in a switch that is 1 gigabit ports for my destinations with a 10 gigabit uplink, right? Those switches are not very expensive, and if you need the bandwidth, that might be a much simpler way to do it. So let me throw another scenario out there. What if I had 2 VLANs and I run one trunk line on each VLAN between the switches? Logically, this wouldn't create a broadcast storm because the broadcast message would be contained to the VLAN. However, this may not turn out as you plan. Older versions of spanning tree protocol would not be VLAN aware. They would simply see that they're going to the same switch and shut down one of the trunk lines, leaving one of these VLANs unconnected. There are switches with newer versions of spanning tree that are VLAN aware, but those are further and fewer between. So when you're building a system like this, do not run separate trunk lines for each VLAN. So what could we do for this? Well, we could turn off spanning tree protocol, that's one option. But another option is to configure a trunk line with multiple VLANs on it. Of course, this configuration will need to be set on both switches. We'll represent that link by candy striping it with both VLAN colors. When a trunk line is set to carry multiple VLANs, it can take packets from each VLAN and add tags to them. The other switch, understanding that this link will carry multiple VLANs, will read and remove those tags as they place the packets back into the right VLANs again. Now, certainly I can set my switches to tag every VLAN that goes down that trunk line. But if I then take my computer and plug it into that trunk port, it won't understand anything that's coming out of there. My computer is not expecting packets to have tags on it. This is extra information, and my computer will then determine these packets are malformed and it will throw them all away. To solve that problem, it's considered a best practice to leave one VLAN untagged. Now if I plug my computer into that trunk port, my computer will behave as if it's on that untagged VLAN. All the tagged packets will be thrown away. And typically what we do is configure that untagged VLAN as the VLAN that has access to the switch's configuration screens. All right, so let's get back to this for a moment. We've taken multiple VLANs and put them on a single trunk line, but what if I needed more bandwidth? Well, we can combine concepts. You can make a link aggregation group of trunk lines. So now multiple cables can move the data between multiple VLANs. Now again, if you've never done this kind of thing before and you'd like to give it a shot, try our managed switch tutorial. It will walk you through the process step by step. Now, just to be clear, don't go to your first installation guide in hand, right? Do that on a workbench so that you can master your craft before you go out into the field. All right, so in summary, VLANs are like breaking a single switch into multiple switches. Non-blocking architecture means the switch is capable of moving all the traffic you feed into it. The switch is no longer the bottleneck, the port speed is. Spanning tree protocol will shut down loops in the network in an attempt to prevent broadcast storms. Link aggregation groups are ways to strap multiple links between switches, garnering more bandwidth. But if you're having to use them in the design phase, it's worth looking to see if there's any switches that might have higher speed trunk lines rather than link aggregation groups. Finally, trunk lines can be designed to carry multiple VLANs by tagging packets between switches. On a trunk line, it's a common practice to have one untagged VLAN so that you could connect a computer, perhaps to access the switch's configuration screens.